So today we're going to be talking about finding a regression equation, specifically a linear regression equation. So regression is a way to kind of model data or take data and try and fit it to an equation that best models and fits that data. So specifically, we're going to be finding linear equations to model our data and try and create an equation out of the x points and y points. So looking at this problem below, I'm not going to read it to you because I'm assuming you can probably read through this yourself. So if you would just go ahead and pause the video real quick and go ahead and read that paragraph, and then you can get me going again. Okay, so as seen, we're looking at global warming. Okay, down below we have the decades and then the average temperature through each decade. Okay. So we are going to write a linear regression equation. So what I want you to do, if you don't already have it open, you can go ahead and open your Desmos calculator. Okay, so you can just go to desmos.com/calculator. Okay, in here, I'm going to show you how to do this linear regression. Okay, So to do linear regression, the first thing we want to do is we want to add a table. So I'm going to hit the plus sign over on the left. You notice as I hit that plus sign, I have a couple of options. I want to add a table. Okay, and so now you see I get an X and Y table. Just like over in our notes, I get my decades and my average temperature, which is X values and Y values. So then over here, I'm going to type in the data just like it is. So 0 through 5 for my X values. So 0, 1, 2, 3, 4, and 5. And then for my Y values, we have 57.164. 57.092, 57.236, 236, 57.668, 57.920, and 58.316. Okay, so now that we have our data typed in, hopefully you notice, okay, and you probably won't see it right away on your Desmos calculator because we're a little out from where you want to be. But see how I have those data points up there? Okay, so what I can do is I can go over here into settings and I can change what my graph's going to look like. So right now you can see on the x-axis we're going from -27 to 89.363. So I can change this to be 0 to, let's go with 6, so we're just a little bit bigger. Don't know why it won't let me. And then on my y-axis, my lowest y value is 57.164. So let's go 55, and my highest is still kind of in the 57, so we'll go 60. Okay. So now, hopefully you should be able to see that I can see my data nice and clearly right there. Okay. The second step that we need to do is we need to add a regression equation. Okay. So to add a regression equation, you can go in here, okay, and we want to type our equation. If you notice up above, we have x1 and y1. So I'm going to use, instead of just x and y, I'm going to use x1 and y1 when typing my equation. So to get y1, you type y and then the number 1, and it will automatically change it to that underscore 1. Okay. And then instead of equals, go here to the capital A, B, C button, and you should see this little squiggly line. It's right under B and N. Okay, this means to estimate. So it's saying y1 is about, and then we're going to do mx1 for slope, and then our x value, and then plus b. Okay, so that's y equals mx plus b, but we're plugging in y1 and x1 for our table, x1 and y1, m for slope, and then plus b. Okay, so as you notice, we now have a linear equation that looks like a pretty good fit to our data, okay, which our data was this table over here, which was our decades from 0 to 5, and those degree temperatures over in the right. Okay, so let's go back to our notes. So we want our linear regression equation. Okay, so we can see the actual graph, but the equation is going to be an equation of y equals mx plus b. So y is equal to something times x. So our m, if you notice right down here in our parameters, we have m is equal to. That's what I want to write as my m. And just to be safe, we're going to round to the third decimal place. So 0.248 for our m. So here, 0.248. And then x plus our b, it tells us right here at the end, 56.946. So that's our nice y is equal to mx plus b equation. Okay. Then our correlation coefficient, your correlation coefficient is an r value. Okay. So if you notice over here, our r value, okay, r is equal to 0.9492. That is the correlation coefficient. So we're just going to write that down. So 0.949 should be good enough. Okay, so let's put some of this information into context. So what is our linear regression equation? We said this at the beginning, but our linear regression equation is not a linear equation in the form of y equals mx plus b, which is our slope-intercept form, that best fits a set of data. Okay, so that is our linear regression equation. Okay, what is the correlation coefficient? So I didn't really talk about what the correlation coefficient is, but the correlation coefficient tells us how good our data is as a fit. But the correlation coefficient, our R value, tells us how good of a fit our regression is to the data. Okay, so a really good R value means we have a really good fit to the data. A really bad R value means we have a very bad fit to the data. Okay, so let's get a little more specific. So this is just kind of what R is in general, our correlation coefficient. But let's get specific, and what does the correlation coefficient specifically tell us about our data? Okay, so specifically, if R is positive, then we have increasing data values. If R is negative, then we have decreasing data values. Okay, so the sign of R tells us if our data is increasing or decreasing. So just to compare that, okay, looking at our data, we went from 57.164 to 58.316. So we can tell those values are going up. We also got a positive R value. So that fits with what we know about the data. Okay, the second thing, and this is really where the fit comes in play, is the closer R is to 1 or -1, the better the fit. To the data. So in our case, our R value was 0.949. So that was a really, really, really good fit to the data because it was really close to 1. And we can see from our graph that our equation, our line, was a really good fit to this data. Okay, so that lines up with what we already know. What we can see from our graph is that our data points were pretty close to our line. See how they're not that far apart and even goes through a couple of them? That means that our line was a pretty good fit. Okay, now let's use this equation to maybe make some predictions. Actually use our equation for something. So using our calculator, we're going to predict the temperature for the 11th decade. Okay, so real quick before I get this, 11th decade, is that an X value or is that a Y value? I want you to ponder on it real quick. Okay, so now let's go back. So 11th decade, if we look at decade number, that's over in our X column. So it's an X value. So what we're going to do is we're going to plug 11 in for X, and that should calculate the temperature, the degree, in the 11th decade. So using the calculator, predict the temperature for the 11th decade. So I would say Y is equal to, and just so I don't get my numbers wrong, 0.248 times 11 plus 0.56, or sorry, 56.946. Okay, and we can type that into the calculator. So I'm going to show you a couple different ways to do that. Okay, so we can type it in to our Desmos calculator. We can just do it right underneath. So adding this in, 0.248, just like we wrote it, times 11 plus 56.946. See how it gives you the equal? It's just calculating that exact value. So we get 59.674. So we can just type that right in here for our temperature in the 11th decade. So equals 59.674. I'm just going to add a little degree symbol for sake. Now, if I want to predict the temperature for the 20th decade, so 20th decade, just like 11th decade, same exact thing, but I'm plugging in 20 for X instead of for 11. So Y is equal to 0.248, parentheses 20, plus 56.946 equals, and then I can just go right here on my equation, and I can erase 11, add in 20, and then it calculates it for me, 61.906. It's not too bad, okay? So I'm just plugging in X to get out a Y value. Remember, X is my independent variable, and in this case representing the decade number. Y is my dependent variable, in this case representing temperature. So temperature is dependent upon the decade number, which lines up with our usual independent dependent of time independent, value dependent, okay? Now the next one, number 3, predict the decade number that will have a temperature of 60.65 or 60.665 degrees. Okay, so in this one, they're giving us a y value for number 3 instead of an x value. So in the last two, I gave you decades. So we plugged in the x value to get the y value. This time, I've given you a y value, and we're going to try and predict the decade. So we're trying to find the x value. So one way we could do this is we could plug in for y, and we could solve it out. But using our Desmos calculator, there's another way that we can solve this, because since I've given you a y value, what we can do is we can go over here to our graph. I'm going to delete this one. Okay, and we can just type in y equals 60.665, I believe was the, 60.665. So we can just type that in exactly as it is, okay? And what it will do, if you notice, it will now graph a line at 60.665, okay? Now, this blue line, we talked about that, that's our linear regression. That's our line of best fit. And then our 60.665, that's the y value we're trying to find. So if I scroll over, notice the blue line is going to start colliding with the black line. Well, eventually, they should come in contact. Okay, and then you can just click on it right here on your Desmos calculator, and it'll tell you. So at 15.002, so I'd say that's probably 15, it gets equal to 60.665. So our x value would be 15. So just kind of as a recap, when we're trying to predict a dependent variable, when we're trying to predict a y value, we're going to plug the x value into our Desmos calculator, and it's just going to give us the number out. When we're trying to predict a x value, when we're trying to predict the independent number, we're going to say y is equal to whatever y value in our Desmos calculator, and then we can just go find the point of intersection where they cross each other. Okay? So let's do another question to practice it. Okay. Table shows monthly record sales of a recording artist over 6 months, and we want to predict the record sales total for December. So I'm going to go back to our linear regression, and we can just go up here to our table. So our x values now, they want us to do January to June, but as 1 through 6. So we're just going to adjust these a bit here. Do we 1, 2, or actually, I'll go ahead and start from scratch, just for those of you that maybe like Mr. Bone, I forgot how you did that. So we're going to start from the beginning again. So I want to add in my table, so plus sign, table, x1, y1. So x1 for our table is the month numbers, 1 through 6. So 1, 2, 3, 4, 5, and 6. And then our y values is the record sales, so 60,000. Just make sure you get the right number of zeros, 54,000. Then 58, 46, 58,000, 46,000, and then 43 and 30. Okay, so my x and y values are super off again now. So my x values go from 1 to 6. Okay, so we want to adjust our graph again. So I'm hitting the little wrench over here on the right. I'm going to change my x-axis to be, let's do 0 to 7, so I can make sure I get all of it. And I'm going to change my y-axis. My lowest y value is 30, so we'll do like 29,000. And my highest y value is 60, so we'll do 61,000. There we go. Now we can see all my points. Okay. So then here in my equation, I type y1 because it's x1 and y1. So y1, and then I want the about equals, just as a refresher. Okay, when you hit the little keyboard button, you hit ABC, and it's going to take you to that little squiggly line, which means estimate. Okay, and then I want mx1 for slope, and then my x values plus b for my y equals mx plus b. So we can see our line going through there. If we click away our keyboard, we can see all the metrics we want, our R value, our M, and our B value. Okay, so going over here, our linear regression equation. And this time we're gonna type it so it makes it a little easier. So y is equal to, we hear our M is negative 5571.43. 43x for our slope. And then for our B value is 68,000. So plus 68,000. And we'll add some spaces to make it a little easier to read. All right, what will be the record sales total for December? Okay, so December would be month 12. So all we're going to do is we're going to take this equation and we're going to replace, x with 12. So over here in Desmos, negative 5571.43 parentheses 12 instead of x plus 68,000, and we get 1,142.84. Record, not record. Record sales. And then last but not least, they want our correlation coefficient. So remember, our correlation coefficient is the R value, which in this case is negative 0.928. All right. A, does this data have a strong correlation or a weak correlation? Well, we talked about earlier that a strong correlation is closer to 1 or negative 1. Negative 0.928 is pretty close to negative 1, so we would definitely say strong. Close to negative 1. And then is this data increasing or decreasing? Well, we have a negative R value, and as we talked about earlier, positive means increasing, negative means decreasing. So our R value is negative, which means this is a decreasing set of data. And we can also just see by, looking at our data, we're going from 60,000 to 30,000, so we're definitely going down. And we can see by looking at our line, we're going down, decreasing from left to right. So it's definitely a decreasing set of data. All right, y'all, that's linear regression. We'll go over this again in class, but please ask your teacher if you have any questions, especially with typing this in and setting it up in the Desmos calculator.